So we're going to start a discussion of behavior detectors by talking about ground truth. The first big issue with developing behavior detectors is, where do you get the prediction labels? How do you know when a student is off task or when they are gaming a system? Behavior labels are going to be noisy. There's no perfect way to get indicators of student behavior that you can completely trust. It's not truth, it's ground truth. Truth is good enough for the current situation. Truthiness even, if you're a Stephen Colbert fan. Another way to think of it, in some areas there are gold standard measures, as good as gold. With behavior detection, we have to work with bronze standard measures. Gold's less expensive cousin. Is this a problem? Not really. It does limit how good we can realistically expect our models to be. If your training labels have inter-rater agreement of kappa equals 0.62, you probably shouldn't expect or want your detector to have kappa equals 0.75. And if you get that, you're probably overfitting in some scary fashion. So is this worth doing? Well, ultimately, as Herb Simon once said, anything worth doing is worth doing badly. And I'm a big believer in this. So where do you get ground truth for behavior detectors? And you note the issue of ground truth is not just an issue of behavior detectors. You can find it in a lot of contexts. But for behavior detectors in specific, you can get your ground truth through self-report, field observations, text replays, or video coding. Self-report is fairly common for constructs like affect, emotion and context, and self-efficacy. It's not as common for labeling behavior. Imagine a self-report item for gaming a system. Hey, are you gaming a system right now? Yes or no? You might wonder, is a student really going to report accurately? Oh yeah, I'm gaming a system. I'm totally not trying to learn here. You may think this is a straw man example, but in fact this was recommended to me by an IRB compliance officer in 2003. Although in fact he didn't even recommend doing a pop-up questionnaire. He actually recommended just asking the kids, hey, excuse me, if you're gaming a system right now, can you please raise your hand? I didn't think that was a good idea. I think that self-report is great for a lot of things. I'm not sure it's great for this kind of behavior that students may not want to admit. A second approach is field observations, where one or more observers watch students and take systematic notes on student behavior. It takes some training to do right. If you're interested in this, you may want to look at the BROMP coding manual. The BROMP approach is the one my lab uses. And we actually have a free Android app that implements it, developed by my group, which handles both the details of the protocol, such as observing the students in the right order and the timing, and handles synchronizing with log files. It's kind of cool, and if you want to use it, it's free. So I encourage you to take a look. A third approach are text replays, which are pretty prints of student interaction behavior from log files. So let me show you some examples to show you what that looks like. In this first example, you can see that the time of each action relative to the start, every clip starts at 0, and the student's input, the context in the learning environment, the system's assessment, and the skill involved. In this case, the student got something right at time 0. 20 seconds later, they moved on to the next thing in the interface, and they said minutes. The system said that's a bug. It's a known misconception. So they said, all right, well, 4 seconds later, how about hour? No, that's still wrong. 7 seconds later, years. That's still wrong. 14 seconds later, week. So what this student is doing is systematically trying every single possible unit. And in fact, we code this as gaming a system. Here's another example. At time 0, the student types 8 plus, and the system says, you're wrong. 1 second later, the student tries 8 plus again, and the system says, you're wrong. 57 seconds later, the student says, maybe you should die. The system says, wrong. The student then requests help, and about 25 seconds later, types a string of question marks, which the system again indicates is wrong. This is probably an indication that the student is frustrated and acting out. It's probably not a happy student. So what's going on with this student? Well, this student's responses are probably not appropriate responses for model identify rectangle prism non-base face, which is a skill in geometry. And I'm going to guess that the student doesn't actually think that these answers are going to work. So probably this student is acting out towards the system. WTF behavior. So some of the advantages of text replays, first of all, it's blazing fast to conduct. It requires 8 to 40 seconds per observation. Decent inter-rater reliability is possible, it agrees with other measures of constructs, and it can be used to train behavior detectors. On the downside, there's a limited range of constructs you can code. Gaming a system? Yes. Collaboration behaviors in online chat? Yeah, Davi Prat has done that. Frustration and boredom? Well, sometimes. You can catch it when it arrives at the point of actually acting out. But off-task behavior outside the software? No. And collaborative behavior outside the software? Also no. Another limitation is it's got lower precision than field observations or other approaches because there's a lower bandwidth of observation. You just can't see everything that's going on. A fourth approach for getting ground truth of behavior detectors is video coding, which can be videos of live behavior in classrooms or screen replay videos. This is the slowest method. It takes a long time to do. But it's replicable and precise. There are some challenges in camera positioning, and if you don't get this right, it can be difficult to code your data. Whichever of these methods you're using, it's good to check for inter-array reliability when you're using an expert coding method, be it text replays, field observations, or video coding. Researchers typically try to shoot for kappa equals 0.6 or higher for expert coding. But ignore magic numbers. Any real signal is something you can try to recapture. It doesn't really matter at some level. Why would you say if your kappa is 0.54, then there's no information we can try to capture? Especially if there's a big impact in capturing something that's a little bit better than chance. Personally, I'd rather have 1,000 data points with kappa equals 0.05 than 100 data points with kappa equals 0.7. You can cut through all that noise if you have more information. And once you have your ground truth, you can build your detector using the methods we talked about the first 2 weeks of class.